Hello, Pascal.
Hello, can you hear me?
Yes, please share your slides.
Okay.
So Pascal Noterdaeme is based at the IEP in Paris, and indeed has been using UVES over the last years to look at tracer of a cold gas, especially molecular tracers, including CO and deuterium-based molecules. And I believe he's going to tell us about this result next. So, Pascal, the floor is yours.
Okay, I hope you can see my screen because I just see my presentation in full screen, so I don't have access to the Microsoft Team anymore. Is it okay?
You're good.
Okay.
Yeah.
Excellent. So first of all, thanks all the organizers for this opportunity to tell you about molecules at high redshift, and thanks Michael to introduce the field already. So here I'm going to talk about molecules as a probe of astrophysics more than fundamental physics. And my talk is organized this way, so I will first introduce the motivations why we looked for molecules in quasars, using the same technique of quasar absorption lines. And I split my talk in two parts. First, UVES as a detection machine, and then UVES as a follow-up machine. And of course, at the end, I will present a summary and prospects and what I think could be improved for this field with UVES. So the motivations before UVES started were based on two main observations. So this very simple way of saying it. It's first that these DLAs, so these strong absorptions that we see in quasar spectra, as you can see in the figure on the bottom right, these DLAs have H1 column densities, which are very similar to that of galactic disk, as we could see at that time at 21 centimeter. And then the other observations that we all know that star formation takes place in molecular gas. And again, since hydrogen, molecular hydrogen is found in our galaxy, so should it also be the case in DLAs? These are really from galactic disks. But before going into the main part of my talk, this is something I would like to remind is we know that H2 is a poor coolant. So why does star formation care about this chemical state of the gas? Why does star formation care whether the gas is in molecular or it's in atomic form? Why it should just care about whether it's dense, cold or not? And the reason, as I explained here below, that the H2 forms onto dust grains, and it has a dependency then on the density of dust and the density of hydrogen, which makes a dependency on n squared times z, where there is a metallicity. And the gas cooling through metal emission lines has exactly the same dependence. Now, if we look for the destruction processes of H2, H2 is destroyed by UV photons, so it goes linearly with UV flux. No, not linearly, but it depends on the UV flux, sorry. And then the heating of the gas also depends on the UV. So basically, the conditions that favor the presence of H2 also favor the onset of star formation. So there may not be direct causality between the two, but rather a correlation. So this is also why it's interesting to look for H2, even if it's not directly in molecular clouds, but just molecular hydrogen. So then the motivations now have changed a little bit. We know that DLAs at high redshift are not necessarily nice, large rotating disks, but it can be more complex. The galaxy were still much more in interaction with intergalactic medium, so you have flows of gas in and out. And we have now many more questions where H2 can help us to understand what's going on. So what are the chemical and physical properties of this gas at high redshift? How does this H1 convert into the H2? And this is extremely important to understand the star formation process, overall star formation process, because you start from the diffuse gas in intergalactic mediums. This has to come inside the galaxies, cool down, convert into H2, further cool down, and then form stars. So this process of converting atomic to molecular hydrogen is one of these steps, and it's very important to understand this. Then, of course, what is a CNM fraction? So CNM is a cold neutral medium fraction, as H2 is a tracer of this cold gas. And then where is this molecular gas located? Where is it inside the disk? Is it outside in the flows? So these are all important questions. What are the ambient conditions? For example, this UV flux, which will depend on the star formation rate. And the good thing with quasars is that you can probe very small scales. As you can see, there is a zoom here where the molecular clouds are still much bigger here than the beam of the quasar. But I will come back to this a bit after. So as Michael nicely introduced, H2 can be directly detected through electronic lines. So these are in the UV. So it's not through a proxy like in the emission used using CO. Here, using quasar absorption lines, we detect directly the H2 molecules. And this is known actually since the 70s using UV satellites, using exactly the same technique, but looking to nearby stars and probing the interstellar gas close to the sun, let's say. And but in the distant universe, well, all these lines are redshifted in the optical, and then we can observe these H2 lines using ground-based spectrographs. And this is where UVES has become very important. So I just put here limits for the atmospheric cutoff at around 300 nanometers. And this implies that we can observe H2 only from redshift above 1.8. So it's quite fun that we can observe more easily H2 at higher redshift than at low redshift. So here, to do a bit of history, I show the first spectrum where H2 was detected. So this spectrum was taken in 1980 by Morton. It was a low resolution. We have a resolution of 1600. And the detection of H2 was done by Levshakov and Varshalovich. And using this spectrum, I don't know how they did it. It was really a great achievement because it's very hard at this resolution. So they compared the tabulated lines found by Morton with H2. And they could detect H2 there in this spectrum, which was confirmed later by different observations at high resolution. So then I go to the second detection. So don't worry, I'm not going to do all the detections one by one, but it was just to show that more than a decade after the second detection was obtained. So here you see a piece of the Lyman alpha forest, and the dotted line, if you can see this, are the H2 model. So this was at twice this resolution of 3,500, and this was only the second detection. So there came UVES, actually, with this resolution of 50,000. And then the blue coverage and the high resolution allowed us to dig really into the Lyman alpha forest and avoid all this confusion. So on the top left, you see the actual UVES spectrum, and then the zoom on this same UVES data, where you can see the Lyman alpha forest now with all these lines which are very well spaced, and the red profile is the absorption from the H2. And you see many bands with many lines. So you see like L0, L1, all these are the Lyman bands, and W are the Werner bands. And the small numbers below each band are the rotational levels of these molecules. I will come back to this in a moment. But here there is absolutely no doubt, and you can really detect H2 with very high confidence, thanks to UVES. So if you consider UVES as a H2 detection machine, so here I made this plot. It took me several hours to do this plot, actually, to come back to the first spectrum of where the H2 was detected. So it's a date of the observation of the spectrum, not the date where it has been identified. So you can see the big one, more than 1 decade between the first and the second detection. And then in green are all the detections that have been made possible using UVES. So you can see that as of today, 60% of the H2 detection at high redshift actually came from UVES. And now we can see also that starting from 2010 onwards, X-shooter started to play a more important role, and I will explain this also in a moment, why it is the case. But interestingly is to show where are these detections located in the NH2 versus redshift absorption redshift plane. So this is what you see in this figure. So with the same colors, UVES in green, X-shooter in orange, and the rest as open circles. And the first thing that you can see is that if you look at the vertical line, it shows that UVES has been able to dig into the forest at very high redshift, where the forest becomes much denser. And this is only possible at the resolution achieved with UVES. So the record is a redshift of 4 point something. by Ledoux et al. And you have a zoom there where you can see all these lines completely unambiguously. And the second point here is that you can also detect H2 at much lower column densities than with other instruments. So this is the horizontal line that I put at 17.5-ish. And you can see that UVES goes much below orders of magnitude. This is in log scale compared to other instruments. So of course, this plot is biased in the sense that with six-shooter, we tend to move to prefer systems with very high column densities that we pre-select them because we are more interested in very highly molecular gas. But all in all, it tells us that we can go very low with UVES and low in column density and high in redshifts. And this is very unique. And this is to illustrate how well UVES can do. So it's another spectrum taken with UVES, and there is on these two small regions in the lime and alpha forest, which are zoomed here below. I don't know if you can see my cursor, but it's hard to see, but there are molecular lines here in the spectrum below, and very, very small lines, but which are identifiable thanks to this high resolution and very high sensitivity in the blue. So this detectability corresponds to a column density of 10 to the 14, and this means it's less than 1 molecule per million atom hydrogen. So it's really a great achievement. So as if I consider UVES as a detection machine and just talking about whether H2 is detected or not, so I've been a number of surveys. So I arrived in the middle of these surveys when I started my PhD with Patrick Petitjean and Cédric Ledoux. And this started to show different properties of these H2 systems. But the first thing is that the H2 detection rate actually was small. So it's of the order now we know around 5 to 10% at most, which means that the gas DLAs probe mostly warm neutral medium. This is very different from what we see in the solar neighborhood. Then the second observation that H2 is more frequently detected in higher metallicity systems. So this is the plot that you can see on the right, where you have the overall molecular fraction on the y-axis against the overall metallicity in the x-axis. And the H2 detections are these black points, while the upper limits and non-detection are the empty squares. So you can see that basically all the H2 detections are in the upper half metallicity. So we can interpret this at that time in two ways. So first say, okay, it's what it is expected because H2 tends to form onto dust grains. So this is what we expected with high metallicity. You have more metal, so you have more dust. Also, we can think about maybe these systems with high metallicity corresponds to more massive systems where you have a higher number of components, and then you have a higher probability of detecting H2. Now, if you look more in details, we now know that H2 are found in systems with high depletion factors. So instead of looking at the metallicity, we look directly at the dust. So the top right plot shows the overall dust abundance. I mean, this is depletion factor. For example, you take zinc over iron, where zinc is a volatile species, while iron tends to condense into dust. And so this is a histogram of the H2 detections. And in white are the non-detections for the DLAs, and in gray, these are the H2 detections. So this is all from UVES, and you can see that typically all the detections are on the right part of the plot where the dust depletion is high. You can see this better in the bottom right plot, where you have the H2 column density against the column density of iron, which is locked into dust, which is missing from the gas phase. And again, all the black points show the H2 detections, and the white empty squares are the non-detections. And here it's very clear that all the detections are at the high column density of dust. But what is really interesting is that unlike what we see in our galaxy, there is no clear dependence in each one. So this you can see on the plot. Here now it's again the black are the DLAs detection with H2 and the white non-detections, and the green are the same for the Milky Way. So empty points non-detection and filled points are detections. So in the Milky Way, you see that there is a transition. So as long as you go above column density, above something like 20.7-ish, you always see H2. which was not the case in the DLAs. So the question was, is there any transition at higher NH1? Should we go to much higher H1 column densities at high redshift to see the H2, to see such kind of systematic H2 and a transition? So there comes the question of why is this due to? Is it due to the UV fields? Is it due to a lower density of dust, lower density, lower pressure? And the question is, where is H1? When you look to a star in the solar neighborhood, you just probe a little part of our galaxy. While when you observe a DLA at high redshift with a quasar, you cross a big part of the galaxy. So maybe part of the H1 that we see in absorption has actually nothing to do with the actual components where we see the H2. So this is where it becomes important to look into more details and not use H2 just as a detection, but also as a tool to probe these physical conditions. So this comes to my second part now, which is H2 of UVES as a follow-up machine. And H2, as I said in the beginning, has different rotational levels, and you can plot what is here, this excitation diagram, which shows the column density of different rotational levels against their energy. And the low rotational levels of H2 are mainly populated by collisions, while the high rotational levels trace the UV pumping or the warmer H2. And these high rotational levels would be very hard to detect, to constrain without UVES, unless you get, of course, very high column density. But in most cases, this is really better constrained with UVES because column densities of these levels are much lower.
Pasquier, 5 minutes.
Okay, I'm a bit slow, but it's okay. So H2 does not come alone. So if we want to probe the physical conditions in the gas and the chemistry, there are other species that come along with H2, like chlorine. And chlorine is very interesting because it tends to get completely neutral as soon as you have a little bit of H2 in the gas, thanks to very efficient chemical reactions. So here on this plot, you see this Cl1 over H2 versus the metallicity measured in the DLAs. And without going to the details, the red points are what is observed at high redshift, and the blue is what is observed in the Milky Way. But this tells us that if the metallicity is more or less constant in the DLAs, but then the molecular fractions in the H2 bearing cloud must be much higher than the overall measured molecular fraction, which means that most of the H1 actually that we see in DLAs are not related to the H2 bearing gas. And there are other species, for example, C1. And C1 is very interesting. It exists only in the dense and shielded environments and is populated by collisions, by UV pumping, and by the CMB. So using both C1 and H2, you can have a handle on the temperature and the density, the UV field, assuming that you know the CMB. Or doing the opposite, if you know everything, then you can derive the CMB from this. This has been done also. But the absorption bands are very complex and the line widths are very narrow. So if you want to constrain this, then high resolution is absolutely needed. It's very hard to do a study of the fine structure of C1 at lower resolution than UVES. So if you can do this with several species which have different sensitivity on the radiative excitation and collisional excitation, then combining all this together, you can have a very good understanding of what are the physical conditions in the gas. And here you can see in the, for example, the density versus temperature plot, that you can constrain the gas density to be around the 2.5 or a bit more here in that case, and the temperature to be cold, it's 100 K. So this is really probing this cold neutron medium. So what is interesting now that if you have this kind of densities and this kind of column densities, then you have a constraint on the length of this cloud and the size of this cloud. For these numbers here, it's 0.3 parsec, but can be much smaller or a bit larger, depending on the exact numbers you get. But what is interesting here, that this size becomes comparable to the size of the broad emission lines regions of the crater. So meaning here you cannot consider the background source necessarily as a point source, but you actually resolve it. So this is illustrated on the figures that you can see here. So if you have a cloud which is on top of the accretion disk, which makes a continuum of the crater, then this is really extremely small, and your line will go down to 0. But if the cloud is smaller than the broadline region, and coincidentally you have an absorption line that falls on this emission line, you may have some flux residual, some light from the crater that doesn't go through the absorbing cloud. And this has been observed. You can see here one example with H2, it's damped, so it should be saturated, but actually it doesn't reach zero. You have 10% of the light that still escapes. And this is not a calibration problem or anything else. Since you have on the both sides of this H2, you can see Lyman and phosphorescent lines that perfectly reach zero. So it's really a physical effect. This is very interesting. So now we can basically reconcile all these observations into a very crude picture you have here. So the large total cross-section of H1, we see very frequently delays, and that the cold gas has very, very small scales, but it's clustered. So in general, when you have one line of sight crossing molecular gas, you see several components. And if you have two lines of sight that go through, one goes through the cold gas, a line of sight which can be very nearby will also cross cold gas. So we have shown this thanks to lens quasars. It was not with UVES, but with Keck. But this kind of picture reconciles all this. For this, you need a very high number of CNM clouds. Think about a fog, for example. You have very small droplets, but overall, when you cross fog, you will cross a lot of these droplets. And now, thanks to all the sensitivities and various molecules, you can really probe the internal structure even of these clouds, and do PTR models of these things, and even go down to the CO absorption. So the first CO absorber detected was done actually with UVES, and here you have an example here. So this is in the red part of the spectrum, but distinguishing all these rotational levels, like for H2, it's only possible again with high resolution. Now the bands, the rotational levels are very closely separated, so this is only doable at very high resolution. So what is interesting is that with CO, this molecule can be excited directly by the CMB, and then you can constrain the temperature of the CMB at various redshifts. But if we want to do an improvement of this, we need to quantify the contribution of collisional excitation. So for example, with the ELT, we should have a very precise measurement of the excitation of CO and get very precise measurement of the temperature. Now, the accuracy will depend on how well we can model the physical conditions. And for this, observing H2 is absolutely needed. So I'm arriving to my summary and then the prospects. So we have now selections that are so efficient that we don't need really UVES as a detection machine. We are now able to detect H2 directly in Sloan spectra, for example, and we have hundreds of these absorbers already identified. But it remains an unbeatable machine for analyzing all this cold gas and go for very subtle effects. For example, you have a figure here that shows Doppler parameter of these lines. You can see it's very small Doppler parameter values against the energy of these levels, and see an increase in this. So there may be a role of turbulent mixes of the layers, maybe H2 into the warm gas, and these are things which are being investigated right now, because it's very important to understand, for example, star formation inefficiency. We know that turbulence is the main contributor to this, that you can store part of the internal energy into turbulence, and then this would explain star formation inefficiency. So for this, we need to go into very, very fine details, and this is only possible at high resolution. So just to mention, I'm sorry if I'm a bit late, we can also go to the quasar environments where the conditions are more complex and the UV field is stronger, so it's harsher conditions. And of course, we can use a gamma ray burst afterglows to probe the H2, but for this, you need to be fast. So this one aspect I did not talk about. And the main is that targets are really too faint. We have observed all the bright targets with UVES, and this you can see how the magnitude, the G-band magnitude changes as a function of the year. I mean, it's different observations, and we really reached the limit of UVES, and this is why we moved to Excitation, but we don't have this access to the physical conditions that well. So to me, what could be improved? The main limitation for us to use UVES is, as usual, is a very long observing time. So for some spectra, we have to expose 10, 15, 20 hours now. So targets are really faint. And the other problem that we need more than one setting to cover all the lines of interest. And if you want to really understand very finely the physical conditions and subtle effects, we need to cover all the lines, not only the H2, but also C1 and CO and metal lines, fine structure, all this. So what could be improved? Of course, it's improving the total throughput, mostly in the blue. And then if you could cover the full wavelength range at once, it will save us basically half of the time. We need at least 2 settings. So the spectral resolution of UVES is really okay. Now we don't need to improve. This is not what we need. For this we have espresso, not for H2, but okay. And we'll have high-res if you want a high resolution of, for example, the fine structure lines. So what I really would love to is to see more efficient UVES in the blue. And in the ELT area, we'll have high-res, so on the ELT, but then it would be very important to dedicate the VLT to the blue. So this is what I put the blue large telescope, hopefully. So thank you.
Thank you, Pascal. So we have a couple of questions. Maybe Rafael Riaz wants to start.
Can you hear me?
Yeah, I can hear you.
Okay, so you mentioned that the H2 forms on the dust grains. So I'm just wondering that with UVES, how far you actually go back in time to observe the high redshift environment where you find evidence for the dust presence.
Yeah, so with UVES, basically we go from redshift 2 to redshift 4. So the highest redshift we could do is, the highest detection of H2 has been done at redshift 4.2. Then the evidence for dust is, there are different ways. So one is the depletion. So you have species that condense into dust and species that don't. So the correlation with H2 there tells us that this is the main mechanism. And we can also test the dust from the reddening of the crater. So for this, we need a flux calibrated spectrum. And in general, for this, we don't need UVES. And X-shooter, for example, that covers up to the infrared is much better. Then you can really see the extension of this of the crater light by the gas in front of it. I don't know if I answered your questions.
Yes, you did. Thanks.
So next we have a question from Ksenia Tarlikova.
Yes, thank you. Thank you, Pascal, for this interesting talk. And I want to ask you about the dependence of the H2 fraction from H1 column density. You showed that in the Milky Way there is no so clear dependence H2 from H1 column density in comparison with high redshifted DLAs. And may this effect can be connected with some selection bias that comes from different observational techniques?
Yes. So one thing I just mentioned is that the Milky Way observations are done to our nearby stars, which by definitions are already in the disk of our galaxy. We're already probing the disk where the pressure is higher, and then we have higher fractions of H2. And then, of course, at high redshift, with these quasar absorption lines, you cross very much longer path lengths through the galaxy. So the overall molecular fractions I showed with, for example, with chlorine, it's actually much lower than the actual molecular fraction if you could probe a smaller path length. So the path lengths are very different when you compare the Milky Way and when you compare the DLAs at high redshift. And then there are other biases. Is when the observations were done in the Milky Way that the H2 and the H1 were not necessarily observed along the same line of sight, meaning that, for example, the H1 column density was derived in emission from 21 centimeters. So you have things like this. Well, this is a bias that appears, for example, for observations of the Magellanic Clouds. So then you have a larger beam for the 21 centimeter, and then you see an emission, and you may not associate exactly how much H1 is associated to this gas. So yes, you have, of course, selection effects. Yes.
Thank you.
So next we have a question from Sandra Savaglio.
Thank you. I wanted to ask, well, first of all, beautiful talk, lots of results. So the small size of the clouds, this is really intriguing because 0.3 parsecs means like one light year, like as big as the solar system. So I wonder, you should be able to see variability because the clouds are moving. So if you are seeing actually individual galaxy clouds, if this is a cluster of clouds, maybe the variability is not so evident. But if you are observing the same quasar after years, you might be seeing different color densities. Did you try that?
Yes, actually, there is a work by Patrick Boisset and Jacqueline Bergeron on this, where they calculated how much this should change. Actually, the changes are very, very small. Even with this kind of very small clouds, you don't expect drastic changes in the column densities, for example.
I don't totally agree with that. Clouds are moving, you know, and they're moving probably faster at high redshift because there's a lot of objects that are more compact and there is a lot of high speed involved. So I think it should be varying because you can actually see vibration absorption lines close to quasars, you know, in AGNs. So because these are small clouds and they move fast, and I don't know, unless your signal is
Okay, so two things. So first here I'm talking about intervening systems. So we are not in the quasar where you have really flows and very high velocities. So if you have typical velocity like rotation velocities of hundreds of kilometer per second, you will not expect much change. Then the point is that we actually try to do this. So there are very good spectra taken at various epochs, like with UVES, we have now 20 years, so we can compare observations.
All right, sorry, I interrupt you. That means probably that the clouds may be not so small because otherwise you would expect variability. This is my opinion.
Again, so you can have a look to the Boisset and Bergeron paper, so they made the calculation. The variation is you expect very small variation, and actually we are looking for this, and for now we don't see it. Now the constraint on the size of these clouds is twofold. So one is from the physical conditions, so we have the lengths along the line of sight, and the other one is from the partial coverage, and both agree. So these clouds are very small. They are very small, but if you move this with a few hundred kilometers per second, then you will have big change, even in time scales of years. You need to move really much faster. I mean, let's say if the 0.3 parsec, okay, it's a light year, right? But you're not moving to the speed of light.
Thank
you're
you.
moving 1,000 times less.
I think this is an interesting topic for further discussion. I would just like to give a chance to Stefano Cristiani to ask a quick question with a quick answer, please.
Yes, Pasquet, you also computed the cosmic H2 omega, which is a fundamental quantity for galaxy evolution. Now, if we compare what you obtained for your surveys to the cosmic H2 derived from ALMA observations, for example, there is a huge difference. It's an order of magnitude and more. So on the one hand, there could be selection effects that you hinted at before. On the other hand, the ALMA observations are typically based on the CO conversion factor, which is calibrated at low redshift. So what is your take about this huge difference in cosmic densities?
Well, the point is that most of the H2 in mass is not in these diffuse clouds. So this is something we showed, for example, with Sergei Balashov. When we detect H2 in absorption, it's typically very low column density. So most of the H2 is in much denser and a higher density clouds. So actually we just see the tip of the iceberg, and that's the main reason. This is the short answer. Then of course I can elaborate, but the short answer is this. In absorption, we just see a very small part of the H2.
Okay. Thanks.
Thank you. Thank you. you everyone for contributing great topics.